Good afternoon. Good afternoon, and welcome to this lecture of electronics, in which we are going to study uh, thyristors, right? So, Unit 4, Paper 1. We'll be completing this at the earliest. So, let me share my screen. Myself, let me introduce myself. I guess my screen is visible. Oh. My screen is visible. Hello. Okay. So, let me introduce myself. Myself, Dr. N.D. Mishram, Head and Associate Professor, Department of Electronics, Sri Mathura Das Mohta College of Science. And today we are going to study instrumentation, that is actually power electronics, right? So, Unit 4, Paper 1, and we call it as thyristors. So, all the devices which we are expecting to complete in this unit are called as thyristors. So, those are related to power electronics. Now, what actually the power means? Power means where we are supposed to use high voltage and high current, right? So in that is called as the power electronics, the portion of electronics where we are dealing with the voltage, the high voltage as well as high current. So the product of voltage and current is called as power, right? So power electronics is those devices which actually uh, consist of the I mean, the power sense of it, which are capable of handling high voltage and high current. Right? So we'll be speaking on that. So what is power electronics actually? So the power electronics is actually, the definition is the electronics applied to conversion of control of electric power, where we call it as the voltage and current. The product of voltage and current is called as the electric power, right? So we are having input power. If you can try to see it in say block level diagram, so we are having power input, and this is controlled by electric power converter, and which is being controlled by the gates, right? And the output is supposed to be also the power of it. So the high voltage and high current, we are expecting it in the output side. Okay, then we are having the more exact definition of power electronics. Like, the primary task of power electronics is to process and control the flow of electric energy by supplying voltages and currents in the form of that is optimal suited for user load. So whatever we are going to connect it at the end of the circuit, that is called as the load, or whatever the circuit we are expecting to drive is called as the load, right? So whatever we are giving in the input, that is power input, and we are having a power processor over here, which are the devices which we are trying to study this time. And there are the controllers which are going to control these power devices, and the output power is coming out of this power processor, which are applied to this load, right? So these are also called as the feedback circuits, according to which they are being controlled, right? So these power electronics actually, we are dealing with the high voltage and high current sort of devices. We are having power electronic devices. We call it as the thyristors. The power electronic devices provides the utility of switching. The flow of power through these devices can be controlled via small currents, right? So this is the most important part of you might have experienced that whenever you switch on your heater, you switch on your press, you have sparks, right? So that switching, that putting on the switch, gets you a high voltage, high current passing through that, and because of it, which we are having sparks in the plug or in the switch also. So that can be controlled, that can be maintained by using this power electronic devices, right? So these flow of power through these devices can be controlled via small currents. So small voltages can control high power of these things. So that those are called as the power electronic devices. Power electronic devices differ from ordinary electronic devices in terms of their characteristics. So the characteristics which are dealing with the high voltage and high current, right? So those are power devices. Then the power electronics, power semiconductor devices can be classified into three groups according to their degree of controllability. So these are only semiconductor devices which we have studied in the last classes. We have completed semiconductor diodes, transistors, and then FETs, field effect transistors, MOSFETs, and also those all are semiconductor devices. And in the this continuation, we'll be studying this power electronic devices. So they consist of some diodes, power diodes we call it as, and then we are concerned with thyristors. This unit is mainly concerned with the thyristors. Those are SCR, ST. I will talk on that. So thyristors latched on by control signal but must be turned off by power circuit. Right. So these thyristors basically consist of SCR, silicon control rectifiers, then controllable switches turned on and off by control signals. Controllable switches which are going to be controlled by minimum voltage and minimum current. So these devices are going to be used by this. Devices are called as the power electronic device. Now the thyristors. So as I mentioned you, the thyristors are nothing but the three-terminal semiconductor devices which is having three junctions, which are having four layers, PNPN, that can handle high currents and high voltages with better switching speed and improved breakdown voltage. So remember this, we are concerned with high voltages and high current, right? So the product of voltage and current is called as a power. So this is called as the thyristors. We study this. Name thyristor is derived by a combination of the capital letters from thyratron and transistor. So combinedly, we are calling it as a thyristor. Thyratron and transistor. So the main completion of this is called as the thyristor. This is the thyristor which we are having. We call it as a SCR. Here you are able to see that we are having four junctions, P, N, P, N. So we are having P-type, N-type material, then P-type again, and N-type material. And in between this, the third layer, we are having a terminal which is called as gate. The above layer is called as the anode, and the lower N-type is taken as the cathode. Okay, so this is the three junctions we are having: junction 1, junction 2, and junction 3. So this is called as a SCR, silicon controlled rectifier. Now why it is called as a rectifier, we are going to tell you. Silicon controlled means which have been controlled by this gate voltage. So it can have a maximum current and high voltage capability to sustain, and therefore it is named as a power electronic device. This is again a semiconductor device, as I told you. This is a P-type material which we have studied. P-type, a positive P-type of a extrinsic semiconductor. Then we have an N-type of a semiconductor. They are clubbed between, and we are having a four layer like this. So PN, NPN, and these are three junctions: J1, J2, J3. In the below, we are having the symbol of that SCR, silicon control rectifier. So it is as good as a diode with a gate terminal. The uppermost is called as the anode, and the negative N-type material is called as the cathode. Right? So we are going to study in depth how it is going connected and all. So thyristor can handle high current and high voltages, which is the basic concern of our topic now. Typical ratings are 1.5 kilo amperes and 10 kilovolts, so which responds to around 15 megawatts that of power handling capacity. So remember, I just mentioned you that we are going to deal with high voltage and high current, right? So the high current is around the range of say 1.5 kilo amperes. Just imagine the current in 3 ampere. The whole appliances of our home are being settled down. So they require only 3 ampere of current, minimum 3 ampere of current. Now in this case, we are expecting to have a current of the range of 1.5 kilo amperes. Just imagine, and 10 kilovolts voltage. So if you multiply this, we'll have a product factor that is around 15 megawatt power. So these devices, thyristors, are capable of handling this. This power can be controlled by a gate control of about 1 ampere only. So the gate control current will be only 1 ampere current. So, and we are expecting to control around 1.5 kilo ampere of current and 10 kilo voltage. Right. So thyristors act as bistable switches. Then it conducts when gate receives a current pulse and continue to conduct as long as forward bias till bias voltage is not reversed. And remember, whenever it is switched on, it's very difficult to switch off. So that is the basic drawback of this thyristors. Once it is switched on, it is very difficult to switch off, right? So we are having 2 or 3 types where we can switch off this thyristors. They stay on once they are triggered and will go off only if current is too low or when triggered off. So remember, once it gets switched on, once the current starts flowing through that, so it's very difficult to switch it off again. So that is the drawback, and we require some more circuitry to switch it off, right? So once it is switched on, then it is difficult to switch it off again. Now, thyristors. So this is what I have told you, that we are having a four-layer junction, and if you cut it into two slices like this, so we'll be having, if you cut it in two parts, so you'll be able to see that we are having two transistors. One is PNP transistor and the other one is the NPN transistor. And this P in between is taken as the gate terminal over here. So we are taking out as a gate. So if you slice it between these two, so we'll be having two transistor like of a structure that is shown over here. So this is the transistor analogy circuit of the SCR, silicon controlled rectifier, in which the above transistor is a PNP transistor, the lower transistor is a NPN transistor. So once it is switched on, then it is very difficult to switch off. So just take a look of this. So thyristors have three modes, and the output, when we connect it to the anode, is connected to forward bias and the positive terminal of the battery, and cathode is connected to negative terminal. Like that we are going to connect it, and when we apply the voltage, we'll have these type of characteristics. So the gate voltage is actually responsible for the current to flow through that, right? So this is the forward characteristics. Here we are having three modes. The forward blocking mode, only leakage current flows, so thyristor is not conducting. So this is that forward blocking voltage over here, which I'm showing it by arrow, and only here the forward leakage current is supposed to flow through this. Remember, the reverse leakage current only flows because of the minority charge carrier. So that small leakage current flows through that. And when you again increase the voltage at this level, all the junctions break down and a huge current flows through the SCR, right? So that is called as the forward conducting mode. Large forward current flows through the thyristor, right? So this is that current, and this is the forward breakover voltage at which the current decreases, the voltage decreases, and a huge amount of current flows through the SCR. Last one is the reverse blocking mode. When cathode voltage is increased to reverse breakdown voltage, avalanche breakdown occurs and large current flows through that. In reverse bias, so this part of the graph is the third quadrant of the graph, which is in the reverse bias condition. Here we are having this red line, and this is the reverse breakdown voltage. If you increase the reverse bias, so we are changing the terminal potential. So negative terminal is connected to cathode, and positive terminal is connected to anode. This is the general connection diagram for forward bias of a SCR. Whereas if you connect it in reverse bias, then the leakage current will flow through that, and if you further increase it at a reverse breakdown voltage, there is huge amount of reverse current flowing through this. So this is the characteristics of SCR or a thyristor. So phase wave, these are the applications of thyristor. Here we have connected to a high transformer. Here we are using a SCR over here, which is gated. So if you apply a sinusoidal wave over here and a high voltage is taken across this secondary of this transformer, then this type of output waveform will be appearing out of this because of the SCR characteristics. So this voltage is there. This is the application of that. We are less concerned of it. Now, as I told you, that once the thyristor is switched on, it is very difficult to switch off again. So we are having these type of methods. We call this as commutation method. So process of turning off a conducting thyristor. So once it is in conduction, it is very difficult to switch it off again. So we are having these two types of commutation, which we call it as force commutation. One is current commutation and voltage commutation. A thyristor can be turned on by applying a positive voltage of about a volt or a current of a few tens of milliamperes at the gate cathode terminal. So slight voltage or a current at gate can switch on the thyristor, but SCR cannot be turned off via gate terminal. So even if you now switch off the gate voltage, the transistor will not be switched off. So we have to do something, some more circuits is to be applied, and then only we can switch off the SCR. if we turn off only after anode current is negated either naturally or using forced commutation technique. So if you reverse the anode current, then only it can be switched off, or say we can have another circuitry which we call it as a forced commutation technique. These methods of turn off do not refer to those cases where the anode current is gradually reduced below holding current level manually or through a slow process, right? So once the SCR is turned on, it remains on even after removal of the gate signal. I told you, even if the gate voltage is just applied, just a small pulse is given to that, still it is very difficult to switch it off on again. So if it is the gate voltage is zero, then also it will remain in conduction. Okay, so we are having this diagram of that. So this is how we can have a negative applied voltage current through the device. The current can be made zero, right? So we are having this turn off mechanism. We'll see this in the coming slides again. So yeah, so commutation can be classified as into two parts: natural commutation and the forced commutation. So natural commutation is something which is naturally over there, right? So this occurs only in AC circuits. Natural commutation of thyristors takes place in AC voltage regulators and phase control rectifiers, cycloconverters. These are some of the devices, and these are some more theoretical portion of it where we require the forced commutation. So we are going to see those circuits also. These are the some circuits of forced commutation. Yeah. So forced commutation is over there, and here these are the current and voltage characteristics where we can have this reverse change. Then, yeah, these are some of the thyristor devices which we need to study, which we are not having these all in our the syllabus. We are having only silicon, triac, and diac. And what there is one more which we call it as UJT, junction transistor. So we are having silicon controlled rectifier, diode and on alternating current, then triode for alternating current. These are some of more SCRs that we have, which we call it a silicon control switch, silicon unilateral switch. They are not in our syllabus right now, so we won't go in depth of that. But yeah, these are some of the thyristor devices which are available as thyristors SCR. Right, so let us start with that. So the first one is the SCR, silicon control rectifier. We have studied this. Silicon control is a synonym for of a thyristor. SCR is a four-layer PNPN device, has three terminals, anode, cathode, and gate. In off state, it has a very high resistance, whereas in on state, there is a small or on forward resistance. Applications: motor controls, time delay circuits, heater controls, phase controls, etc. This is the circuitry construction of SCR, PNPN. We are having three terminals: anode, cathode, and gate. This is the symbol of that. And this is the transistor analogy circuit which we have studied over there. So we have studied that. Then if the positive pulse current at the gate turns on Q2, providing the path for IB1, right? So if you connect a small voltage over here, a small current over here, right? So we'll see that, yeah. So this is that diagram, the transistor analogy circuit, and here you might be able to see this. This is very simple to understand. So this is a transistor, and it is having a collector which is connected to the gate, as I told you, and the same is given to the base of the transistor Q. So as you are applying the pulse, a simple pulse to the gate, then what happens? This transistor Q2 will become on, and as a result of which it will start draining the current from Q1. As soon as it starts draining the current from Q1, right? So it will again be more forward bias, and the base, this collector will again drain some more current. As a importance of this, more current will start flowing through this. As a result, even if you remove the gate voltage, the SCR will not be switched off. That is what I mean to say. So this is the base example, and these are the characteristics. These are forward characteristics of SCR. You are able to see that IG2, IG1 is greater, IG2 is greater than IG1, and IG1 is greater than IGO, and IGO is equal to zero. So this here it requires a very high breakover voltage, forward breakover voltage over here if gate voltage is zero. and here gate voltage is increased, so we will have a breakdown earlier. If it is further increased, then it can have a further switching off on of this SCR. As you are able to see a maximum current flowing through this. This is called as the holding current, right? So holding current 1, holding current 0, holding current 2, depending on the gate voltage. Okay, so this is how the SCR is used for conduction. As you see over here, we are having anode voltage plus V, and cathode is connected to ground. Here RA is connected as a load, that is the load resistance over here, which is connected. And to just switch on this, we require a simple pulse over here. This is the gate pulse that are being applied, a high pulse. And as soon as we get this high pulse, the transistor on, and then it continuously becomes on. As you can see, the transistors are connected to each other. So there is huge amount of current flowing through this transistor. And once it is switched on, then it is very difficult to switch it off, right? So notice that gate current controls the amount of forward breaker voltage as shown in this graph. The SCR can be turned on exceeding by forward breaker voltage or by gate current. So here we can see this over that. So as you go on increasing the gate voltage or gate current, see we are having the breaker voltage decrease. So that is the description of the this forward characteristics of SCR. Okay, so yeah, then we are having how turning SCR off, how we are going to switch off the conducting thyristor. The SCR will conduct as long as forward current exceeds. There are two ways to drop SCR output conduction. One is anode current interruption, or the other one is forced commutation. Let us see those circuits. What are those circuits? So those circuits are anode current. The first one is if you switch off this anode current, automatically the transistor SCR will be switched off. Yes, it is so. So that is the anode current. So how we are going to switch off? Just by putting a switch in between this. So switch off as soon as you break this connection or break out this. There is no current flowing through this, and then the SCR will be switched off. This is the simple method. Now remember, this is conducting. Now once it is given a gate voltage, it is in conduction. So once it is in conduction, it is not, we are not able to switch it off even if we are applying a low gate voltage. Okay, so even if you have not removed this gate voltage, still it is in conduction. So for switching it off, right? So even if it's switching off, we require that this gate voltage, this anode voltage should be switched off, or we can have another circuitry in connection. So we'll be providing a low resistance through across parallel to this SCR so that the current flows through that, right? So as soon as we switch on this, then the current will not flow through this SCR, but it will flow through this circuit, right? This is a natural phenomenon. So as soon as we flow this current through this other, then the SCR will be switched off, right? This is the natural commutation, and then the forced commutations, in which we are using a transistor over here. So we are using another battery over here so that the current will flow through this like this. And in that circuit, we can have a transistor, right? Okay, so yes, yeah, this is the forced commutation. So here we can apply a small transistor and we'll try to flow the current which was earlier flowing through this SCR to flow from here, right? Then we can switch it off. So a transistor, just through a base, we can apply some voltage and the transistor will be switched on. Transistor as a switch, remember that circuit. Okay, so this is the circuit of that, and these are the characteristics of SCR. So these are some of the characteristics: forward breaker voltage, voltage at which SCR enters forward conduction, that is on region. Holding current is value of anode current for SCR to remain in on region. Then gate trigger voltage, value of gate current to switch SCR on. And average forward current, that is maximum continuous anode current, that is DC, that the SCR can withstand. Right, reverse breakover voltage, here it is reverse breakover voltage, maximum reverse voltage before SCR breaks into avalanche, that is called as reverse. So these are some of the definitions. These are some of the SCR applications that we are having. So SCRs are used in variety of power control applications. One of the most common applications is to use it in an AC circuits to control a DC motor or appliance, because the SCR can both rectify and control. Definitely. So SCR is triggered on the positive cycle and turns off on negative cycle. SCR circuit like this is useful for speed control for fans or power tools and other related applications. So we are having this in our day-to-day life also. So this is how we can use it, the SCR. So these are some of the applications. The second one is the triac. Now remember, as you have studied SCR, this SCR only works in one direction. So that is why it is called as say a rectifier, which conducts only in one positive half cycle, right? So triac, in the other case, this triac is now a 5-layer SCR in which we say that we are having two SCRs connected back to back, right? So when we connect two SCRs back to back, one SCR will conduct in one direction and the other SCR will conduct in another direction. This is the construction of that triac. Since we are having two terminals, which can be anode, either anode or a cathode, so we call them as MT1 and MT2. Main terminal 1 and main terminal 2. The gate is connected to both the SCRs, common to both, and they are being connected to the gate. Like so, we call it as two SCRs which are connected back to back. We are having again three terminals, MT1 and MT2. In our fan regulators, that rotary fan regulators, we are using SCR. So we use SCRs daily, right? So this is the triac. Now, if you connect it to positive or negative in both the cycles, it is going to conduct, right? So this is the SCR, right? These are some literature over here, and yeah, I guess we are having some characteristics of SCR. So two thyristors which are connected back to back, as I've told you. So the triac can be considered as two thyristors connected in anti-parallel as shown in the figure. The single gate terminal is common to both thyristors. The main terminals MT1 and MT2 are connected to P and N regions of the device, and the current path through the layers of device depends upon the polarity of the applied voltage between the main terminals. The device polarity is usually described with reference to MT1, where the terminal MT2 denotes that terminal MT2 is positive with respect to terminal MT1, right? So this is a 5-layer circuit. Yes, yeah. So this is that two SCRs which are connected back to back. Oh no, this is a die. Sorry. Yeah. So this is there is no circuit, I guess. Yeah. The last one is diac. I guess we will complete this in the next class. So we have studied today about the SCR and a triac. We call them as a thyristor family, and this is actually the graph of SCR. The same is the graph for SCR also. Sorry, triac also. So it will work in both the directions, right? So this is the characteristics we will have in triac also. So thank you very much for joining. I guess this much is enough for today. We'll be having more lectures on this. If you have any problems, you can, yeah, you can say unmute yourself and ask me questions. Have you understood? Thyristors, SCR, and triac. So SCR and triac are same. SCR only works in one forward bias. Triac, we are having two SCRs which are connected back to back. So both the currents flows through in both the directions. So we can have AC voltages coming out of it. So the diagram is same as we have seen it in forward bias. So if there are no questions, do you have any questions? Yeah. So since there are no questions, we will conclude here. Thank you very much for joining. Stay tuned to my YouTube channel. Go through my YouTube channel, watch my videos. I'll be uploading more videos of electronics on my YouTube channel. Please like, share, and subscribe my channel. Thank you very much. Have a nice time. Take care. See you soon. Stay home, stay safe, take care.